What's going on, everybody? This is Mr. Diamond, and we're going to be working through our two example problems from Chapter 4, Section 1. We're working through Example 3 and Example 4. I already did Examples 1 and Examples 2. So for Example 3, we have... okay, I thought I clicked on the wrong one. We're good. So we have a 900 kilogram car with velocity of 10 meters per second. 10 meters per second is our velocity. Goes around a circle with radius equal to 25.0 meters. And this is 10.0 meters per second, and this is 900 point, just for sig fig purposes. Don't want to make sure we miss those pieces. And then the question is, what is the acceleration and what is the force felt, or force acting upon the car? Now, first thing you want to do for all of these, it's not going to be super relevant for this one, but as always, draw a picture. The later sections we're going to get into, having a picture is going to be very, very, very important. But this one's kind of simple, so I'm just going to do a square as my car. Say we're looking at it from a top-down view, and we'll say that it's going to take a turn, and that if we were to expand this turn out, it would have a radius of 25 meters. And the reason we want to do this is just so we're making sure that we're clear about what's happening. In this problem, it's not going to be super relevant, but I like to make sure that I want to make sure that you guys are still in the habit of drawing the pictures so we can make sure we know what everything is, where everything's at, all of that. Gravity would be acting on the car, the normal force would be acting on the car, all that stuff would be happening, but we don't really need it for this problem. Okay, so looking at what we're given, we are given kilograms, we're given a velocity, and we're given a radius. Well, we conveniently just talked about our equation. Acceleration in a circle is equal to velocity squared over the radius. And we have both of those pieces of information. So we can go ahead and just plug them in. 10.0 meters per second is going to get squared. That's going to be on top. And then our radius is 25 meters. Notice that we'll have a meter squared, second squared, divided by a meters will leave us with just a meter and a meter on top, and then a second squared on the bottom. You can plug this in, but this is just 100 divided by 25, which is just 4. And it'll be meters per second squared. So that's our first piece. We just plugged it into that equation, and we're good to go. For the second piece, we want our force. We aren't very clearly given anything this chapter, but I did mention in the notes, and you, as always, may be asked to use formulas from previous chapters. We're just going to be using F equals ma. We just calculated A, so F equals ma is going to be 4.00 meters per second squared times its mass, which is just 900 kilograms. And kilograms per meters per second squared, or kilogram meters over second squared, sorry, it's going to give us newtons. Plug this in, you will just get 36,000 newtons. Again, you can do this in your calculator, but 4 times 9 is 36, so 4 times 900 would be 3,600. So that's bare bones, basic, most straightforward possible question. You're just plugging it into acceleration using acceleration for F equals ma. The next one we're doing is going to be a little bit trickier, just a little bit. It'll involve some more algebra skills. So now we're going to have, for question number 4, we're going to have a merry-go-round, and I'm going to go ahead and draw my circle as best I can. And then on our merry-go-round, we are going to have a person. So I'll draw my little stick figure. Let me make sure I'm in. Excellent. Okay, so our mass is 45 kilograms. The radius r is equal to 4.00 meters. There's also 45.0 kilograms, which I'm actually adding this. So those of you that are only watching this video in class will, or watching this example in class, will have the proper sig figs. Okay, 45.0 kilograms, 4.00 meters across. And then we know that the force in this problem is going to be 9.00 newtons. Now again, thinking of the things that are relevant to this question, we could be checking for the gravity, we could be checking for normal force. Those would both be acting on this thing, but it's not going to be relevant in this problem. You'll see why later, but the short version is because we know that the force already is there. We only need to start bringing those in if we're missing some of the pieces of information. The question wants us to find our period and our frequency. Those are the two things that we are looking for. Okay, so how do we solve for those? Well, starting from the top, we're given force, and we know that force is equal to mass times acceleration. We have a mass, we don't have an acceleration. To get these, we need, most likely, if we're not just trying to solve directly for them through some other weird means or just plugging in unknowns, we're going to be trying to get to our velocity equation, because our velocity equation will give us t, which will give us f. If we know one, we'll know both of them because they're inverses of each other. So we need velocity. We don't have velocity, but we have radius. We don't have acceleration, but we have force. And force can allow us to solve for acceleration, which will allow us to solve for velocity, which will allow us to solve for period. So if F equals ma, we want to find our acceleration. Our acceleration is equal to our force divided by our mass. Our force is 9.00. Our mass is 45. We get, again, this one's actually pretty straightforward. 9 by 45, that's 1/5. Or 0.2 meters per second squared. So that's our acceleration. Next step, we have our velocity equation, our acceleration equation. Acceleration is velocity squared over radius, and we now have acceleration. We also have radius, so we want velocity. Velocity is equal to the square root of AR, or in this case, the square root of 0.2 times 4. Which gives us, that one we will want to plug into our calculator, square root 0.2 times 4. We get 0. It's a little hard to see, so I apologize for that, but 0.8944279191, blah, blah, blah. It's probably more after that, but I usually do the blah, blah, blah before I do the whole number. Oops. But we can plug that in, because we know velocity is equal to 2 pi r over period. And that is what we're looking for. We're trying to find period. So if I rearrange that, I can get t equals 2 pi r over v, or 2 pi 4, because it's our radius from over here. It's 4. And then over 0.89 ... I'm going to just use the whole number. I'm also going to simplify this and just do parentheses. We'll do not second first. We'll do 8 pi over we'll do over answer. It's a much more efficient way to do this. Move it down here so we can see a little better. We get our period is 28.099 ... So t, if I round it to an actual answer for sig figs, our t equals 28.1 seconds. So that's how long it takes for one full rotation. F is equal to 1 over t, which equals 1 over 28.099 ... which equals, if we plug that in, 1 over second answer, 0.35588 ... which equals 0.0356. 1 over seconds, or inverse seconds, or that's how many rotations happen in 1 second. 28.1 seconds to do one rotation, or 0.0356 rotations happen every 1 second. So really just solving backwards with algebra. I know I probably may have confused some of you by just bringing randomly in, like, oh, we're doing the force diagrams. Like, we will need them a little bit more later on, but notice that we never needed them for any part of this. Even though this force that we're talking about here on this turn, and the force actually keeping them in place here, is also friction. It's the friction of their butt keeping them in place on the merry-go-round, or the friction of the tires keeping them on the road. We didn't need to solve anything related to friction. We actually could have used it to try to solve for frictional force or something like that, for example, but we haven't yet. That's where we're going to go in the next section. In the meantime, though, if you got any questions, This has been Mr. Diamond. Have a great rest of your day, everybody.